Jnanam Paramam Dhyayam. Knowledge is supreme.
Alright, so now in this lecture, after discussion with the associated prime support, etc., now we will come to what is called primary decomposition. This is a generalization of a prime decomposition that we will see it once we have defined it what it is precisely. So let us first define it what it is. Definition. So always let A be a Noetherian ring and V A module and U a submodule of V. Alright, now a finite family Qi, I in I is a finite indexing set of submodules of V which are primary submodules in V. That means the homotheses are either injective or nilpotent, and this Qi will be primary corresponding to some prime ideal. So finite family of submodules is called such that the given submodule U is intersection of these Qi's. This is called, so this equality, so this is called a primary decomposition of U in V. So now there are several questions will come up, namely whether does it exist, is it unique, and so on. So but before that, as I said, I just want to say that this is a generalization of the prime decomposition. So we'll look at this example. So suppose A is a PID. For example, you can take either A equal to ring of integers or a polynomial ring in one variable over a field K. Then we know that if I take any non-zero element x in A, x non-zero, then we know that this x has a prime decomposition. That means x is a product of some unit times some p1 power nu 1 pr power nu r, where u is a unit in the ring and these p1 to pr are prime elements. That means they generate, each one of them generates a prime ideal, and these nu 1 to nu r are the multiplicities, that is bigger equal to 1, and they are distinct prime elements because equal ones we have collected together. So such a thing is called a prime decomposition of a non-zero element in a PID. We know that in such, because PIDs are UFD, so every non-zero element has a factorization like that. Now when I translate this in terms of the ideals, that means ideal generated by X, that is this will go away because ideal generated by that is A. So this is A P1 power nu 1 intersection APR power nu r. This becomes intersection because the product and intersection is same when the ideals are co-maximal, but because they are distinct primes, these ideals are co-maximal API and APJ for distinct I and J. This is the whole ring A for I not equal to J. Therefore, this equality holds, and moreover, because they are prime elements, these APIs are prime ideals. Not only they are prime ideals, they are actually the maximal ideals because they are non-zero prime ideals in a PID. Non-zero prime ideal in a PID is maximal. Therefore, they are maximal ideals. Therefore, their powers. Therefore, A pi power nu I, these are API primary ideals. Therefore, what this equality is nothing but it's a primary decomposition of the ideal AX. So this equality is a primary decomposition of the ideal generated by X in the module A. So that is the reason why it is called, therefore it is the generalization of the prime decomposition. So in a ring may not be UFD, but whether the question is whether in general rings, ideals in the ring have primary decomposition, and the answer is yes if your ring is Noetherian. All right, now we prove prove the existence. So that is the theorem. This theorem, which is called existence of primary decomposition. And for the proof of this, we will use the earlier construction of the associated primes and so on. So let A be Noetherian, A be a Noetherian ring, and V finite A module, and W a submodule, or U. U is, I said U, no? U is a submodule. U is a submodule of U. And then there exist finitely many submodules Q1 to QR submodules of V such that the following holds, such that 1 QI is PI primary. In V, and these PIs are different. PI not equal to PJ for I not equal to J. They are prime ideals. So PIs are prime ideals in the ring A. Okay, that is one. Second, U is intersection of Q1 to QR. And third, the associated primes of V by U is precisely this set P1 to PR. So, if you want to find the associated primes, you will find the primary decomposition and look at their corresponding prime ideals, and those will be the associated prime ideals. So, this is the theorem we are going to prove. There will be several steps, but all are easy. So, for a proof, note that we can assume u is 0. This is you by passing from V to the residue class module V by U. Then we can assume u is 0. And then when you go mod that, then the primary decomposition will be Qi by N. Alright, then okay, so we can assume u is 0. Now suppose we want to construct this Qi, right? So suppose now the third condition is associated primes of V u are precisely P1 to PR. So therefore, suppose we know already associated primes of V, these are finitely many prime ideals. So let us say they are P1 to PR, and then we want to construct Qi's so that Qi's are P primary and they are different, and u 0 equal to the intersection of Q1 etc. QR. That is what we want to prove, because we already know 3. Alright, now suppose this, then by the earlier the lemma, I can construct. So by earlier theorem, which says that given any subset, you can find, given any subset of the associated prime, you can find a submodule whose associated primes are precisely the given set. So by earlier theorem, there exists for each I, Qi, a submodule. This is for each I equal to 1 to R, such that the associated primes of V by Qi is precisely the singleton Pi, and associated primes of Qi, this will be removing Pi. So this is P1 to Pi minus 1, and then Pi plus 1 PR. This is for every I 1 to R. There exists such a submodule, because that is what we have proved in the earlier theorem, that such a submodule exists. Now first note that we have checked that once the associated primes of this is singleton, then we have checked that such a submodule has to be Pi primary. So note that Qi is Pi primary in V. And now put u equal to Q1 intersection Qr. And what would you like to prove? Now we want to prove this u has to be 0. That is what we want to prove. Alright. So to prove u is 0, this is what we want to prove. Alright. So this is equivalent to proving If I want to prove some submodule is 0, I want to prove that the associated primes of this U is empty, is empty set. There is no associated prime. That's what we have noted when we defined associated primes. So we want to show this. Okay, all right. In any case, we know associated primes of U. This is contained in associated primes of Qi, because this is the submodule of each one of them. So this is submodule. This is associated primes is a subset here, and this Qi is a submodule of V. Therefore, this is a subset of associated prime ideals of V, and this is true for every I from 1 to R. So, if this has some element, so therefore I know therefore, and this we know it is P1 to PR. So therefore, if at all this contains some, we want to prove it is empty set. If at all it contains some element, it must be one of the Pi. So note that if Pi belong to associated prime ideals of A in U, then Pi will also belong here. Then Pi will also belong to associated prime ideals of Qi. But I know I have chosen Qi so that the associated prime ideals of Qi are precisely omitting Pi's. So this is, we know we have chosen Qi so that this is P1 to Pi minus 1 and then Pi plus 1 to PR. So therefore Pi definitely doesn't belong here. So this is a contradiction. So this means, so there this proves that associated primes of U should be empty set, and that is equivalent to saying U is 0, and once U is 0, we have proved everything. So that proves the existence. Alright, so this proves the existence. Now the next job is to find the uniqueness. Alright, so now we are precisely defining what does one mean by the uniqueness. So let us define. So this is a definition. So this will tell more precisely what does one should mean by uniqueness of the decomposition. So again, a Noetherian ring. Remember that our assumption is V is a finite module. So V, a module, finite, and U is a submodule of V, submodule. And we are talking about primary decomposition of U in V and its uniqueness. So the primary decomposition, U equal to Q1 etc. intersection QR of U in V is called irredundant if all are necessary. That means what we can also, if there are two conditions. One, there exists, so intersection of Qi, Qj, j not equal to I, this is not contained in Qi for every I. For every I this thing happens. That means this Qi is really necessary in this intersection. And second condition, the associated primes of V by Qi this is singleton Pi and this P1 to PR are distinct, are pairwise distinct. That means, so that is Pi not equal to Pj for I not equal to j. Then we only say that it is irredundant. That means all the P's are different and all the capital Q's, they are needed to in the intersection. Now let us prove a proposition. So proposition. So let U equal to intersection Qi, I is from 1 to R, be an irredundant primary decomposition of U in V. V is a finite modular Noetherian ring and this is a primary decomposition. Then 1, the associated prime ideals of Qi by U, this is the union of the associated prime ideals of Qj mod U, the j is running not equal to I and j is from 1 to R. Alright, and B, 2, the associated prime ideals of V by U is precisely the union of associated prime ideals of V by Qi. If it is redundant, then this must be these two equalities. So proof. So each are equalities. So one, I would like to prove one inclusion at a time and then the other inclusion at a time. Okay. So so I am proving one and that to this inclusion. This inclusion I am proving. That means every element of this should be an element in this union. That is what I want to prove. So, all right. So let us take the given U is you take intersection over j not equal to I and then Qj and then intersection with Qi. So I have separated out that I because I want to prove that if somebody is an element here, then it is here. So the j is from 1 to R. So this I just rearranged it. So because of this, what do I know? This U is equal to the intersection of these two submodules. Therefore, if I want to look at the associated primes, so therefore associated primes of Qi mod U, this is contained in associated primes of, I have to take union over j not equal to I, j is from 1 to R, associated prime ideals of Qj mod Qj intersection Qi. Since because this inclusion follows because I have the inclusion map from Qi mod U to the direct sum Qi mod Qi intersection Qj, and this is running over J not equal to I, and here also this should be I. So this is clearly an inclusion, because if somebody goes to 0 here, that's in the intersection of each one of them, therefore it is, so that is easy to see. Therefore, if I look at Qi, this one, Qi mod Qi intersection Qj, this is isomorphic to Qi plus Qj mod Qj, which is a sub of V by Qj. Therefore, this one is clear. Therefore, associated prime ideals of Qi by U, this is contained in the union J not equal to I, associated prime ideals of V by Qj. So that proves one inclusion, and the other inclusion is will be clear by 2. So I just want to prove 2. So the other inclusion in 1 will be clear from 2. So proof of 2. All right, proof of 2. All right. So what is that we want to prove? We want to prove that the associated prime ideals of V by U is contained in this union. So look at the associated prime ideals of V by U. We want to prove that this is contained in union. Union is from I equal to 1 to R, and the associated prime ideals of V by Qi are singletons. They are singleton PIs, because Qis are PI primary. So this on the other side, so this is clearly contained there. Now other inclusion, so this is clear, this is clear. On the other, conversely, if you put Pi equal to intersection Qi, now this is running over J, Qj, J running J not equal to I, J is from 1 to R, then Pi intersection Qi is given U, and therefore and Pi is not equal to U, because it was irredundant primary decomposition, and again therefore Pi by U, this is non-zero, and this is contained in Pi plus Qi by Qi, which is contained in V by Qi, and therefore we get associated prime ideals of Pi by U is singleton Pi, and because Pi by U is contained in V by U, therefore all these PIs belong to the associated prime ideals of V by U. So we have proved that equality here. So that proves equality here, and that proves the proposition, and therefore we prove that irredundant primary decomposition exists, and we will still deduce one corollary from this. Let me write that corollary, because corollary. So a Noetherian ring, a Noetherian, V finite A module, and U is a submodule, then there exists a primary decomposition of U in V which is irredundant. So, in fact, what we do is, so if U is the intersection Qi is a primary decomposition, Qi Pi primary, then PIs are uniquely determined. And they belong to they are precisely elements P in the associated prime ideals of V by U. So, that proves the irredundant primary decomposition of a submodule exists in a finite module, and maybe in the next time I will deduce the uniqueness, what one means by the uniqueness of the primary components. So, we will do that in the next time. Thank you very much.